Well, first I want to thank the organizers for putting on such a fantastic event and allowing us to speak about all the things that I think matter for the future. And specifically for allowing me to connect to one of the themes of the beginning panel, or what makes me hopeful. And for me, what makes me hopeful is the connection of AI and science. And that's what I'm going to be talking about here today. And if you remember only one thing from this talk, if there's only one thing that you sort of carry with you in your mind, I want it to be this. And when we write the history of AI in 100 years, it will be the history of how artificial intelligence rekindled a renaissance in science and allowed us to discover more things and to satisfy our curiosity in more ways than we ever thought was possible. So that's the core message here. AI as an engine for science. Now, artificial intelligence is by no means a new field. It was founded a long time ago, and I think one reasonable point to start with is the Alan Turing paper in 1950, Computing Machinery and Intelligence, in which Turing describes this question of whether machines can think or not. The field has developed fast since Turing wrote this, as the video suggested, and it's been fascinating to follow all of the different things that have happened in just the last 10 years. Turing's basic question was this. I propose to consider the question, can machines think? What the field has done since Turing asked this question is to show that one of the things they really can do is they can help us think. They can think with us, they can create with us, and they can be curious with us. That's new, and that's something that I think is tremendously powerful in a lot of different fields. When we think of a technology, we typically have some kind of idea in our heads. We think of the technology in metaphors. And when we think about artificial intelligence currently, the most prevalent metaphor is that of the chatbot. And chatbots are great. They can be super helpful. They can help you find things and learn things. And I encourage you to visit the Google booth outside where you can see Gemini, one of our chatbots, and test and try it and work with it. There's a lot that chatbots can do. But that's not the only metaphor that we should use. It's not the only image we should have. Another image that I think is tremendously powerful is that of AI as a scientific instrument, a new kind of scientific instrument. A microscope allows you to see things that are really, really tiny. A telescope allows you to see things that are really far away. Artificial intelligence allows you to see things that are incredibly complex in fairly simple ways. And it's a very specific kind of instrument that also accelerates the pace at which we can do science and discovery. And I want to give you an example that I think is sort of the most powerful example and something that we've worked on for quite a time. And that is something called AlphaFold. And AlphaFold is, for those of you who are not familiar with the technology, is something that enables what is called protein folding. And that sounds horribly nerdy, I know. But it is incredibly powerful and interesting for the very simple reason that we are largely made of proteins. They are the building blocks of life. And figuring out how proteins work, what they do in our bodies, how they connect, that's essential to curing disease, finding new drugs, understanding life at its very basic levels. So protein folding is something that's really, really hard. The reason it's hard is not that we do not know what proteins are made of. We know exactly what they're made of, amino acids, and we know two-dimensionally how they're connected. But in order for that knowledge to be useful to us, we need to understand the three-dimensional structure. It's like Lego pieces. If I just tell you how many dots there is on a Lego piece, and not how they're organized or in what order they are, that Lego piece won't be useful to you. You won't be able to understand what to do with it. But if I tell you exactly how they're organized, you can say, oh, I can build different things of this, or this connects here or connects there. It's the exact same thing with proteins. What you want to do is you want to understand the three-dimensional form. And that used to be a very hard problem. So hard that you would give it to PhD students if they've been naughty. You say, you go away and fold the protein. And they would fold the protein, and it would take 4 years for them to do this. And you could get your entire PhD on the basis of folding a protein. And this was very hard to do, because at the very small level that proteins act, it's hard. You can't see them because there are quantum effects that make everything fuzzy. So it used to take 4 years. A couple of years back, we published AlphaFold that came with a database of 200 million folded proteins. That's almost all of the proteins there are. And if you now do some calculation in the back of an envelope, you realize that if it used to take 4 years for one protein, and we published 200 million of them, that's 800 million years of time. That's a lot of time. And that's what artificial intelligence allows you to do. It accelerates the pace of science. And even if I'm wrong by a factor of 100, it's 1,000,000 years of time. And that's still an enormous acceleration of science. In the latest iteration that we released now recently, called AlphaFold 3, we've also expanded the database to cover DNA and RNA and interactions between these different molecules, so we can start to we can get an inkling of what it would mean to read life. And that's extraordinary. And we need it, because science is slowing down. This is one of the dirty secrets of our time, and that is that scientific productivity has been dropping for the last couple of decades. Science is filled with data, filled with complexity, but we don't have the means or tools to address that complexity. And that is what AI can do for us. Suddenly, we can reignite science. We can restart scientific productivity. When we do that, we have to be mindful of how we approach science. Science is not just sort of about throwing compute at a problem. It's also about structuring our own questions. We have to ask the right questions to unlock the right knowledge. And the way we think about this at DeepMind is that we think about it largely as finding root node problems. Problems that, if we solve them, unlock entire fields of research in different ways. And I'll give you a few examples shortly. But in order to do this, we also need to come together as a society. And we need to figure out, how can we curate our data better? How can we make different scientific domains readable for this technology? And there's a huge collective, collaborative piece of work here that needs to be undertaken for us. We need to make the world readable for artificial intelligence. And when we can do that, we can start addressing these root node problems that in turn will unlock science. I'll give you a few examples of other things. We're not just working on proteins. We're working on a couple of other projects as well. And amongst some of the more exciting are the following 4. GNOME, which is research into materials science, trying to figure out how many different kinds of materials can there be. This seems like a very basic question, but if you unlock it, if you unlock materials science, you will be able to search the space of possible materials for better batteries, better solar power, more sustainable materials, materials that are more durable, that can be used in different ways to improve security and safety of, for example, vehicles. And here we published a paper just before Christmas that expanded the known number of materials that you can search through by a factor of 100. Another problem that has been haunting mankind for as long as we've been around is weather and predicting the weather. This is something that's also tremendously hard to do. But with GraphCast, another of our projects, we've been able to predict weather on a 10-day scale much better than before. And this makes a huge difference for example, agriculture. When do you put your seed out? When do you harvest? Those kinds of things are directly determined by weather. And if we can improve weather prediction, we can do a lot of things that will allow us to improve agriculture, and that will allow us to feed more people. Alpha Missense, a project where we're looking at the genome and what generates disease. So if we can start to look at the human genome and predict where disease starts, we can also stop it. This technology is incredibly promising and promises also to look at hereditary diseases and perhaps help fight them in different ways. And lastly, the big one, the one that if we unlock this is such a root node problem that it will unlock so much else: fusion. Imagine energy almost at the cost of zero, being able to harness fusion, essentially giving everyone their own personal sun if they want it. And I think that's something that if we can make progress there, and AI has made significant progress on the problem of how to control the fusion process, we can create wonders. This is something we need to do together. This is something we need to do as a society. The progress from artificial intelligence to science and discovery to social and economic progress draws on what is the most powerful in us, our ability to be collaboratively curious. And organizing that curiosity, using the technology we have, is one of the great opportunities for the future. And I'm very much looking forward to doing that with all of you and everyone else who's interested in the future of science. Thank you so much for your attention.